Hello, this is Dr. Gardner. Today we'll be working on a tutorial on how to name acids and bases. Well, we're going to spend most of our time naming acids. You'll find that naming bases can be quite simple as long as you've mastered how to name ionic compounds first. So let's consider what an acid is as we begin. Acids in water tend to produce hydrogen ions. For example, if we consider hydrochloric acid dissolving in water, as it dissolves in water, it's going to ionize to produce hydrogen ions and chloride ions surrounded by water molecules. To be a little more specific, the hydrogen ions tend to combine with water molecules to form hydronium ions, which have 3 hydrogens, an oxygen, and a positive charge. Basically, one proton, that hydrogen ion, is added to a water molecule to form those hydronium ions. For shorthand notation, you'll notice that chemists will often just abbreviate the hydronium ions by showing the hydrogen ions when we look at our acids. Now, first of all, the simplest types of acids we have are those similar to HCl, hydrochloric acid. Well, these are called binary acids when there's only 2 elements present in the formula as we're writing them. So, if we imagine that our anions set end with an IDE, those that are monoatomic, as they form acids, they're going to have a hydro prefix added to them and an ic suffix. Those will be binary acids. Now realize if I see that hydro prefix, you should not be showing me an acid formula with an oxo anion present. They should be an acid formula with one of my monoatomic ions, or at least one of my simple IDE anions, as we'll see here shortly. So let's see how I might build the name for a binary acid. So I'm going to start with the element that it is the basis for the monoatomic anion that I have added a hydrogen ion to the front of, added a proton to the front of. I will add the prefix hydro, and the element name I will change to have a suffix and ending of an ic, just like we saw with the hydrochloric acid. So here's another example of that. Let's replace the element name, though, by the root name of the element we're going to use. So let's use fluorine first. I'm going to change that element to fluorine, and so I'm going to add the prefix hydro and change the suffix, the ending of fluorine, to ic. So hydrofluoric acid is a binary acid. You will notice there is no oxygen in this formula, just HF. If it were to dissolve in water, we would expect to have hydrogen ions being produced as well as fluoride ions from this compound. It is very reactive and can be considered quite dangerous, even though it's not classified as a strong acid. It's quite reactive. Now, if we have sulfur as our root element, well, then I would add the prefix hydro and then change the ending of the name for sulfur to ic, so hydrosulfuric acid. If you recall, the sulfide ion had a -2 charge. That might remind you that I need 2 hydrogen ions, so H2 at the beginning of the formula, in order to balance out the overall charge in a sense. Now as that ionizes, we're going to get the 2 hydrogen ions as well as sulfur for hydrosulfuric acid. Now if my base element is bromine and there's no oxygen present, so it's still a binary acid, we would call that hydrobromic acid. See, these are all quite simple, learning how to name. So let's look at a table that summarizes some of the simple acids we should be able to name at this point. So we've already seen hydrofluoric acids originating from the fluoride anion, but now we have an acidic proton at the first part of the formula. Now if we consider chloride as my root anion for the acid, we could have hydrochloric acid. These are all binary acids, only 2 elements present in the formula. If bromide is my root anion, I have hydrobromic acid as the acidic form. If I have iodide, it's hydroiodic acid. All of these have an anion that they originated from with a -1 charge. I want you to notice that they have a single hydrogen in the formula of the acid, so that charge will relate to the number of hydrogens in the binary acid formula. Now next we're going to look at one of our exceptions to the IDE rule. Do you recall we had a couple of those? Like hydroxide, cyanide, the peroxide ion. We're going to look at cyanide next. Now cyanide has a -1 charge, so we're only going to need a single hydrogen in its acid formula. Now even though cyanide is not a monoatomic ion. We're going to treat it as a binary acid for the purpose of naming. So we're going to call it hydrocyanic acid. So we're seeing these IDE endings going to X, and we're seeing a hydro added to the beginning. So this is hydrocyanic acid. Now, again, if we look at sulfur and we have sulfide, the sulfide ion has a -2 charge, so its binary acid form would be hydrosulfuric acid. So those are quite simple to remember once you've practiced a couple. So just to review one more time, if I have HCl, since it's binary, I need to use the prefix hydro. Now be very careful. Students will frequently make the mistake of trying to use hydro at the beginning of their acid names when they have oxo anions present, and we will not use hydro in that situation. We only use hydro when we're dealing with these simple ide anions that we've already learned. So here I would have HCl, that would be hydrochloric acid, just a simple binary acid. HI would be hydroiodic acid. Okay, and I could go ahead and do all of them in that table if I wanted to practice some more, so continue practicing with those, but they're fairly simple to remember. Now what we want to look at next are once we have oxo anions as the basis for our acids. So these are going to be called oxo acids or ternary acids as we start to have 3 elements present in their formulas. Okay, so we're going to have hydrogen present in the formula at the beginning of the formula usually, oxygen, and then a third element in the formula. So let's see some of these. Now we're no longer using hydro. That was for my binary acid, so we're leaving that off. We're not adding a prefix right here yet, though we may use other prefixes in just a little bit. So I'm going to use the element root, and then I changed my suffix to an ic, but there's no hydro there, so I shouldn't confuse that with hydrochloric or the other binary acids. Okay, so let's choose some of our common 8 anions we've used before. We had sulfate. You remember sulfate had a -2 charge, so its acid formula would have 2 hydrogens in the front and be a neutral formula. So I'd write H2SO4, and I would take the root element name of sulfur and change the ending to an ic, so it would be sulfuric acid. So if I'm seeing that ic and no hydro, I'm thinking there's an oxo anion present. It must be sulfate because sulfur is my root name, so it's sulfuric acid. Now if I had chlorate as my root anion, then its acid would only have 1 hydrogen because the chlorate ion has a -1 charge. So the acid will only have a single hydrogen in the formula. I would call it chloric acid. So you notice my sulfate and chlorate have gone to sulfuric and chloric as acids. Now if I had carbonate, it would go to carbonic acid. The carbonate ion had a -2 charge, so there's 2 hydrogens in the acid formula. If we consider my chromate ion, it was one of the metal oxo anions I asked you to learn. The chromate ion would go to the chromic acid. Since chromate had a -2 charge, there's 2 hydrogens in the chromic acid formula. Note that the name is quite simple. Even though it has hydrogen and oxygen present in the formula, there is no extra reference from the name to hydrogen or oxygen. I just have to remember they're coming from the oxo anion basis, and the 8s are going to X here. Now sometimes you've been hearing me say oxo acids. They're also called oxyl acids on occasion, so you may hear either one. Now there's a few common ic acids you should know. I'm going to give you a list of 7 of them. We've already listed 4 here, so let's add a few to that list. So here we have chloric acid, bromic acid, iodic acid. Those all look pretty similar. And then I have nitric acid, carbonic acid, sulfuric acid, and phosphoric acid. Okay, they all have a formula with the number of hydrogens equivalent to the charge on the oxo anion they originated from, right? Because chlorate had a -1 charge, so there's only 1 hydrogen in the acid formula. Bromate had a -1 charge, so there's only 1 hydrogen in the acid form of the ion. Iodate had a -1 charge, so there's only 1 hydrogen. Nitrate, -1 charge, only 1 hydrogen. Carbonate ion had a -2 charge, so we have 2 hydrogens in the neutral formula of the acid. Then we had sulfate, which had 2 negative for the oxo anion, so its acid formula has 2 hydrogens. The phosphate ion had a -3, so I would have to have 3 hydrogens present in its formula. Now, with this in mind, we can see how the prefixes and suffixes can relate between oxoanions and their acids. If I've memorized the 8 oxoanion, as I write the acid, the 8 ending goes to an ic. So chlorate goes to chloric acid, or nitrate goes to nitric acid, or sulfate goes to sulfuric acid, for example. I can also have acids with a variable number of oxygens and use my prefixes of per or hypo, or the ending, if I had an ite oxoanion, would go to an us for the acid. So for example, if I had chlorite, I would have chlorus acid to tell the difference with respect to the number of oxygens in the formula. Okay, let's look at a couple of these. Let's look at the chlorate formula. If I've memorized that chlorate is ClO3-, I know that chlorite has 1 fewer oxygens and hypochlorite has 1 less oxygen than the chlorite formula. And perchlorate would have 1 more oxygen than the chlorate formula. This follows as well for the acids. Now I want you to notice, if I have chlorate memorized, the acid formula, the 8 just changes to an ic, and we added a number of hydrogens equivalent to the charge of the oxoanion. So I added 1 hydrogen, so I end up with chloric acid being HClO3. Now if I have chlorite, though, we need to differentiate the suffix, the ending of the acid name. So instead of being an ic, it goes to an us. So you can remember 8s go to ics, ites go to us's, right? Let's repeat that one more time. That's pretty important to remember. 8 oxoanions produce acids with ic as the ending, the suffix. 8 oxoacids produce us's for the acid name. So I end up with chlorate going to chloric, chlorite going to chlorus. So if I wanted 1 fewer oxygens than chlorite, we knew the anion was called hypochlorite. Since we have an ite suffix here, we're going to have an us. So we have hypochlorous acid. Now if we had 1 more oxygen than the chlorate formula, we had perchlorate. The 8 goes to an ic, but I keep the prefix, so I go to perchloric acid. So let's practice this again. So I had chlorate. Recall the acid name. What was the acid name? The 8 goes to an ic. So I have chloric acid. The charge on the chloride ion was a -1, so I have 1 hydrogen in the chloric acid formula and no charge shown. It's a neutral formula for chloric acid. If we have chlorite, well, chlorite has a -1 charge and 2 oxygens. The 8ite indicates 1 fewer oxygen. And then as we go to the acid form of it, we have ites going to us's, so we have chlorous acid, HClO2, same number of oxygens as the chlorite. If we have 1 fewer oxygen, we go from chlorite to hypochlorite ion. And then the acid formula would keep the prefix, but the ite would go to an us. So we have hypochlorous acid. We have ClO at the end of the formula, and only 1 hydrogen at the beginning because the anion charge was a -1 here. Now if I had 1 extra oxygen from the chlorate formula to go to perchlorate, we would see that the acid would be perchloric acid. Again, the 8 goes to ic, and we kept the prefix. So we end up with the acidic hydrogen, only 1 shown because the charge on the oxoanion was a -1. And then we have 1 chlorine and 4 oxygens, same number of oxygens as the perchlorate. It's just we end up with perchloric to tell the difference with the acid. Now I'm going to show you how learning to name 7 common oxoacids, going from the 8 oxoanion to the ic acid, can help us generate a variety of acid names. And I'm not really memorizing them. I'm just learning the rules for how changing the prefixes or the suffixes relate to a variable number of oxygens. That's all I'm doing. I didn't really outright memorize the others. I just followed the trend. Okay, so if we start with our base name, let's see which of our 8 oxoanions you might be expected to be able to relate to an oxoacid. Okay, so my chlorate would be chloric acid, my bromate would form bromic acid, my iodate would form iodic acid, my nitrate would form nitric acid, my carbonate would form carbonic acid, sulfate would form sulfuric acid, and phosphate would form phosphorus acid. So I should have all of those down just from the anion name. I just changed the ending from an 8 to an ic. And my number of hydrogens at the beginning of the formula is equivalent to the charge on the base oxoanion. That's why where phosphate had a -3 charge, I ended up with 3 hydrogens in its formula. Where sulfate had a -2 charge, I ended up with 2 hydrogens in its formula. Carbonate had a -2, so I had 2 hydrogens. All of the other oxoanions shown here had a -1 charge, so they have a single hydrogen in the acid formula. That's really quite simple to remember once you start relating it that way. Now, if I were to remove an oxygen from any of these acid formula names, so if I subtract one oxygen, you remember that the 8 oxoanion went to an ite, right? But 8s go to ics as acids, and what did ites go to as the ending or the suffix with respect to acids? Ites went to us's, right? So all of these acid names with one fewer oxygen in their formula would be the us acids. So chloric acid, if I subtract one oxygen from the formula, would be chlorous acid. And it works for the whole series. So chlorous acid, bromous acid, iodous acid, nitrous acid, carbonous acid, sulfurous acid. These are swapped actually. There's a typo there. This should be phosphorus acid and the other one should be phosphoric acid. I will correct that on the posted PowerPoint. Sorry for that. Those are reversed. But you can see that the S's were the ite forms of the oxoanions. We have one fewer oxygen. Now if I have 2 oxygens that I've removed from the formula, well, when we had the anions, we went from an 8 to an ite to hypoite. We keep the prefix with the acid, but the ites go to us's. So we end up with having hypochlorous acid, hypobromous acid, hypoiodous acid, hyponitrous acid, hypocarbonous acid, hyposulfurous acid, and hypophosphorus acid. Just one less oxygen than was present in just the us form of the acid, and 2 less than the ic form of the acid. Now if I add the prefix per, it means the same thing that it meant with respect to my oxoanions. So I would add 1 oxygen and have a per element name ic acid. So per chloric acid, per bromic, per iodic, per nitric, per carbonic, per sulfuric, and per phosphoric acid. They all would have 1 more oxygen than the base ic acid form had, where my 8 oxoanion originated from it. Just remember, I'm just adding my hydrogens to the front of my per 8 anion. So like per chlorate goes to perchloric acid, and these are all neutral. The number of hydrogens are equivalent to the charge on the original oxoanion. So you have a little worksheet that's posted on Blackboard where you fill out some tables with these to kind of practice and work on memorizing these general trends with prefixes and suffixes. Just remember that 8 oxoanions go to ic acids and ite oxoanions go to us acids. That's really the trick behind that. So let's practice a few of these together. Let's practice naming a few oxoacids. So what would be the correct name for each of the following acids if you looked at the formula? Okay, so here I have HNO3, and what's going through my head is, since there's an oxygen in the formula and it's more than 2 elements, this is a ternary acid, so I'm thinking I should not use hydro. I should not use hydro because there's oxygen as part of the acid formula. Okay, so I leave hydro off. Then I have to think, what is the oxoanion I have present as part of this formula? I see NO3 and a single hydrogen in the front, so I'm thinking that looks like nitrate with a -1 charge. I added a hydrogen to the front, so it's neutral. So we can see that would be nitric acid. So nitrate went to nitric. 8 to ic, 8 to ic for my acid. Now if I look at the next formula, if I see H2SO4, I'm looking at the end of this formula. I have SO4. That looks like sulfate, and that would fit my charge being 2- for the anion, and I have 2 hydrogens in the acid formula. So the sulfate would be named as an acid. The 8 goes to an ic. It's sulfuric acid. Okay, and then if I were to look at the next formula, HNO2, I have to be careful here. We already had the nitrate ion, right? We had the nitrate ion as our first example. This oxo acid has one fewer oxygens. So I knew nitrate, if it loses an oxygen, goes to nitrite. And I know that ites go to us's. The nitrate went to an ick, right? 8 to ick. Here nitrite goes to us, so it's nitrous acid. Nitrous acid. Now if I look at the next formula, this looks similar to sulfate when we had sulfuric acid's formula, but we have one fewer option. So the sulfate would go to a sulfite for the last part of the formula. And since we lost an option, that ite would go to us, so that would be sulfurous acid, for example. And then here I have HNO3. We lost another option, right? From when I had my nitric, I lost one when I went to nitrous. Now I lost another option. We keep the OUS ending, and we end up adding hypo, because if you look at the end of this formula, this looks a lot like the hyponitrite ion. So this would be hyponitrous acid. Now actually we get a slightly more complex formula that occurs in nature, where we have two of these units combined, so the molecular formula has two hydrogens, two nitrogens, two oxygens. Don't worry about that right now, but for naming purposes we could start to make a prediction with the formulas we're looking at. Now what if I had one more oxygen in nitric acid's formula? So if I had HNO3, that's nitric acid, if I add an extra oxygen to form HNO4, how would the name change? Well, I would add a per to it, right? That would be like the nitrate ion going to per nitrate. So I go to a per nitric acid. Do you see the general trends? So go ahead and, if need be, use the table we looked at previously to help yourself study, or try to produce the table on your own by using your prefixes and suffixes. I want you to note that all of these oxo anions, none of them have hydro in the name. If you add hydro to the name, you're indicating a binary acid without oxygen as part of the formula. So be very, very careful. So for the last little bit of the tutorial, we're going to look at naming bases. Now naming bases can be quite simple for many of them, because they will follow some general rules we use for naming ionic compounds. So if we're going to name bases, well, I can remember bases tend to in water dissolve and produce hydroxide ions. So for example, if I have sodium hydroxide, NaOH, I named the cation sodium. And the anion hydroxide, as it dissolves in water, we get sodium ions surrounded by water molecules. The oxygen atoms would surround the cations. The hydrogens would start to surround the anion of hydroxide as it dissolves in water. Now we can have weak bases like ammonia. Now when we see ammonia, we don't have the hydroxide ion in the formula, so even though many of your bases will have hydroxide shown in the formula, some of them will produce hydroxide when they react with water. So here ammonia reacts with water. It actually takes a proton from water to form the ammonium cation. Here to the right hand side is one of the cations you should learn. And then I produce hydroxide. That's what's left over from the water molecule. Now this is only happening to a very small extent with ammonia and water. It's a weak base, so only a very small percentage of it is producing this, but there is a little bit of hydroxide. So this we would categorize as a weak base. Ammonia is a weak base. Sometimes you'll see it listed as ammonium hydroxide, even though that's a minor form in solution. Now, if I want to name bases, many of them are named just like ionic compounds. Ammonia was an exception here. Other carbon-based compounds, or if you recall, carbon-based compounds can be categorized as organic compounds. Some of them, if they have carbon, hydrogen, and nitrogen, will act like ammonia and produce weak bases like we saw with the ammonia here. But we're going to focus mostly on metal hydroxides as the other bases you should learn at this point. So realize that sodium hydroxide, NaOH, you just name the cation first, followed by the anion hydroxide. Very simple. So if I had calcium hydroxide, we have the calcium cation. It has a +2 charge, so I needed 2 hydroxides here. I showed the hydroxides in brackets to indicate that I have 2 of them. And then I show the 2 as a subscript outside. That 2 affects everything inside the brackets. I have a total of 2 of those hydroxide ions within the brackets to balance charge. Now, if I had an iron 3 hydroxide, how many hydroxides would that require in order to balance the charge? It's iron 3, what's the charge on the cation? It's a +3 charge, right? My symbol for irons, capital F, lowercase e, is a +3 charge. I would know that it was 3 hydroxides. So I have brackets OH around the OH and a subscript 3. Now the old-fashioned naming for iron 3 was a ferric. That would be ferric hydroxide. Now I can also look at ammonium hydroxide, but I said that was the minor form, so a lot of times I'll just show ammonia NH3 for labels of solutions because that's the major species in solution in water. But if you see NH4OH, we know that's ammonium hydroxide. Name the cation first, followed by the anion in all of these cases. So if I had a zinc hydroxide, the cation would be shown first, then the hydroxide ion. And zinc has a +2 charge, so I should show 2 hydroxide as part of the end of the formula. But really, that's all there is to naming bases. They're quite simple. The oxo acids are a little more challenging. You'll spend a little more time on them, but probably you'll master naming bases fairly quickly.